I meant to break this slide up into several sub slides, but I guess I forgot to do it before I saved it. So we're going to talk about oscillations, and I brought some demonstrations. Those of you who have had lab, played around with these same kinds of things. Let me put them on the table here so hopefully the camera can see them. The two big examples are a pendulum. I know on the camera you can't see the top of this pendulum, but it's swinging from a point. What you see in the lab is essentially what's called a simple pendulum. A simple pendulum has essentially a massless piece of string and then a point mass at the bottom. So you don't want a big, long, extended mass. Right? I could hang a meter stick from here and have the meter stick oscillate, and we would say that's a kind of pendulum, but it's not a simple pendulum. Simple pendulum, all the mass is concentrated at the bottom. And there are various things that might affect the motion of this. One is the amount of mass. Another one is the length of it. And then another one is how far I pull it to the side. And I might measure that in angle. I could call the central position theta equals 0, and I might pull it 20 degrees to the side and let it go, and it's going to oscillate. We're interested in oscillations in this chapter. We'll talk a tiny bit about pendula, but mostly we're going to talk about masses on springs. So another kind of system important in physics is a mass connected to a spring. We could have the mass and the spring horizontal sliding on a frictionless table, but our table is not very frictionless. So I'm going to put it vertically, which seems to make it more complicated because there's a spring force and there's a gravitational force. We'll talk about how you can just think about this in terms of a spring force. So there's a position where the spring force balances out the gravitational force on the mass and it just sits there. And if I pull it up or pull it down and let it go, it oscillates. And the first thing that we'll probably notice about this is that there's a certain period of time it takes to undergo one complete oscillation. That means complete up and down motion for this, or a back and forth motion for the pendulum. That's called the period. Same symbol, capital T, that we used for orbital motion. The idea with the period is there's something that repeats over and over again. Here it's the back and forth motion. For planetary motion, it was that circular motion, but anytime something repeats, we tend to use the symbol T and call it the period. Okay, so the period of the oscillation is the time for one back and forth motion. And you can we're going to think of a different way to represent the period, but we're already, maybe for this particular motion right here, it looks like it's a little over a second for the spring, the period to go, down, 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 down. It's probably just a tiny bit over a second of a period there. We can think of in SI units, the period, you could characterize it by saying it's the number of seconds per cycle. A cycle means one complete back and forth kind of motion, or up and down, or left and right motion, however it's oscillating. But there's a different way of characterizing the same thing. If we know the number of seconds per cycle, instead of telling you that, I might tell you the same number in the number of cycles per second. So for example, if the period is 2 seconds, that means it takes 2 seconds to go up and down. Then what we call the frequency, and the symbol for the frequency is F, is just the number of cycles per second instead of the number of seconds per cycle. So if it was 2 seconds for a cycle, then it's a half of a cycle every second, right? And so the SI units are cycles per second, but we tend to give a shorthand unit for that of Hertz. HZ is the symbol after I assume he's a German scientist, Hertz. So frequency is specified in Hertz in SI units. And of course, the two are reciprocals of each other. So if we know T, we just take 1 over that to get F. If we know the frequency, if we know the period, we take 1 over that to get the frequency. And so that's one way to characterize the oscillation. Second thing that you can see about oscillations is they all have a kind of amplitude. That's how much is going up and down. A bigger amplitude motion means a lot more motion, either side to side for the pendulum or up and down or side to side for the mass and the spring. And the amplitude might sound like it's the distance from the highest position to the lowest position, but it's not actually that. The definition of the amplitude is there's some middle position for the pendulum. That would be when it's right hanging straight up and down. The amplitude is the distance from there to the rightmost or leftmost position as measured in angle. So the amplitude would be measured in angle. Maybe it goes from plus 20 degrees to minus 20 degrees as it oscillates. And so we would say the amplitude is 20 degrees, not 40 degrees. Same thing for the mass and the spring. There's some average middle position, and the amplitude is how far from the middle position to one extreme side or the other. Okay, so it could be a distance or an angle. We're going to concentrate mostly today on the mass spring system rather than the pendulum. So let's imagine a mass, we'll call it M, connected to a spring of spring constant K here. And I'm going to imagine this thing sitting on a frictionless table, so we don't have to worry about energy loss due to friction. We'll ignore air resistance. And in this case, if I remember that by definition, x equals 0 is the position we're keeping track of on the mass or the spring when the spring is relaxed. So the spring would be relaxed, say, if the center of mass were out here at x equals 0. Someone has compressed the mass in to some x position minus a. It's going to be the amplitude of the motion because we're going to let it go from rest at x equals minus a. So you compress it in there, let it go from rest, and at that moment, the speed is 0, and the x position is going to be the negative of the amplitude, because the amplitude, of course, what's going to happen when you let it go from rest, it's going to oscillate between minus a and plus a, back and forth. And the amplitude is just half of that. So the initial position must have been minus a. If we keep track of the potential energy stored in the system and the kinetic energy stored in the system, at this instant when we let it go, it's not moving at all. So there's no kinetic energy. The bar is supposed to be down there at 0. It's all stored in potential energy. So it's got a lot of potential energy at time t equals 0. Now let's watch it move. A little bit later, of course, the spring starts to decompress and it passes x equals 0, and it's got some speed as it passes x equals 0. But by definition, x equals 0 is when the spring is totally relaxed. Right? So the spring, it's hard to tell from the picture, but you're looking here as it's passing by this position. If we're calling it x equals 0, by definition, that's when this spring is neither pushing nor pulling. It was pushing the whole way until this moment, and it's about to start pulling as the mass moves to this side, but it's in between pushing and pulling there. So the potential energy stored in the spring is 0 there. Oh, and I forgot to remind you, the potential energy formula for the potential energy stored in a mass spring system is 1/2 kx squared. And here it is at x equals minus a. So x squared is just going to be a squared. So at this point, there's no more potential energy stored in the spring, and the mass is moving quite a bit. It's flying past x equals 0. So it's got some speed, and so there's 0 potential energy, but there's a lot of kinetic energy in the case. And we can use our old friend, the net work done by external forces equals delta KE plus delta PE, where the spring force is an internal force, and maybe the gravitational weight force and the normal force are external forces, but in any case, they're not doing any work as it goes back and forth because they're always acting perpendicular to the motion. And there's no friction, so that would do some work, but there's no friction. We're imagining totally frictionless system. And so what that's going to tell us is that the kinetic energy plus the potential energy equals 0. I'm sorry, the change in kinetic energy plus the change in potential energy equals 0. And what that means is the kinetic energy plus the potential energy is always equal to a constant. So here, whatever number we had for the total mechanical energy, 1/2 kA squared, that's going to equal the 1/2 mv squared that it has as it's passing x equals 0. And this picture I stole from the web, it labels it as V max because notice V was 0 over here, and it's speeding up the whole way on the way to x equals 0. And then as the spring starts pulling on it, when it goes past there, it starts slowing down. So its maximum speed is when it's passing the spring's equilibrium position. Okay, here it is. It's moved onward farther to x equals plus a. It's at the maximum amplitude position. And again, it's come momentarily to rest. It's about to start going to the left. No kinetic energy and all potential energy. Same potential energy stored here as there was up there. And more generically, we might draw it centered at some position x that's not at either the 0 position or at the maximum position, but at some other random x value here. So some x in between 0 and a. It's got some kinetic energy and some potential energy, right? Potential energy is just going to be 1/2 kx squared, and the kinetic energy is 1/2 mv squared. And the question that we want to ask here is, to start out with, is what is the speed here? Can I calculate what the speed is, given that I know how far I pushed it to begin with? In other words, if somebody tells you that they pushed it to x equals -3 meters, and then they tell you what x it's at as it's passing that position, could you calculate what speed it's at? And the answer is yes. We could say this is our initial case up here, and this is our final case down here. And we could say that the total mechanical energy, kinetic plus potential, doesn't change. And so the total kinetic plus potential initially is equal to kinetic plus potential finally. And I'm sure this must appear on one of my slides, but let's just write it on the board. Let's take our initial case to be where it is compressed and at rest, right? In the final position, it's at some random position x. And so we could say, again, same system, the change in kinetic plus the change in potential energy has to be equal to 0. Let's expand that out a little bit. This would be 1/2 mv final squared minus 1/2 mv initial squared plus 1/2 k x final squared minus 1/2 k x initial squared. We did a lot of that back in chapter 6, right? Now, if initial is when I released it from rest, how does that simplify my stuff up here? Yeah, initial speed is 0, so I can just throw this one away. And we also said that the initial x, we know from looking at the picture, that's going to be the negative of the amplitude. And so the initial x squared will be the amplitude squared. The minus sign goes away. Okay, so let's try to simplify that a little bit. I want to solve for v final. Our goal was to figure out what v was at some arbitrary x. Okay, so let's rearrange some things. 1/2 m v final squared is equal to, if I put this stuff over on the other side, let's see, this will come in with a plus sign. So I get a 1/2 k x initial squared minus, this one was plus over here, I'm going to bring it to the other side with a minus sign, 1/2 k times whatever that other random x is. X final is that random position x. And I want to say, if you give me an x, I want to compute what v is. Okay. And now let's continue solving. I guess the easiest thing to do is first let me multiply both sides by 2, because I've got a factor of 1/2 everywhere. And then I can divide by m and take the square root. All right, let me simplify a little bit more. I've got a common factor of k here. Got a common factor of k. I've got, when I divide by m, I'll have a common factor of m. And let me also factor out an a squared from the front of there. And what I'm going to have is 1 minus x squared over a squared before I take the square root. That's v final squared. And then when I take the square root The square will go away. I'll get a square root there, and I'll get a square root over this stuff. Okay, not the most scintillating derivation, but we can now say, if I release it from rest with it, or if I know what the amplitude of the motion is, then you tell me any other x, I can tell you what the speed is at that point. We got that from just conservation of mechanical energy. Kinetic plus potential doesn't change between initial and final. There's an interpretation of this thing. Oh, well, let me just ask you, can you tell me what the maximum speed is in terms of K, M, and A just by looking at this formula? What is the formula for the maximum speed that's ever attained by the mass? This tells me at any x, how can I make this formula as big as possible? Is it as big as possible when x equals capital A? Doesn't seem like it, right? When x equals A, what's under the square root? It's a 0, right? If x equals capital A, that's when it's either farthest, farthest in or farthest out. Then the speed is going to be 0, right? So, and that makes sense, right? When we plug in x equals A, we get 0. The maximum speed is going to be when, well, okay, we're taking the square root of something here. We want to make this thing we're taking the square root of as big as possible. And to make it as big as possible, we want to subtract off the least amount possible. Right? If you want to make something large, you want to subtract off something as little as possible. And since everything's being squared here, the way to minimize this is just to make x equals 0. So when I plug in x equals 0, this is 0. I get the square root of 1, which is 1. So this thing that whole thing turns into 1, and I get the square root of k over m times a. So this thing that's sitting out in front, sometimes people write this, and you probably saw it in the book. They'll write that sometimes as just V max out in front of that square root. Okay, so that's an expression that allows us to calculate the speed of a mass oscillating on a spring at any position in the oscillations. Okay, let's go back to the screen now. I think there's some voting questions here. Okay, so in this case, we're drawing a picture as if we pushed it in by a certain distance. Maybe I tell you what A is. Imagine that we instead stretch the spring not to a distance A, but we double the distance we stretch it. So if we compressed it 1 meter, now we're going to stretch it to 2 meters. How does that affect the total mechanical energy stored in the system? What that means is kinetic plus potential at any time. Here we wrote down something about the change in the total energy, the kinetic plus potential. That just means 1/2 mv squared plus 1/2 kx squared. How is the total energy going to change if we double? Maybe I'm not giving anything away if I say we double the amplitude, right? Doubling the amplitude. I'm not getting a strong vibe that everybody's ready to vote, but if you've got to vote, hold it up. It's very quiet in here. Everyone's just staring intently at the screen. Okay, those who are voting that I see are all voting by A. Can you tell me your reasoning about how, so, it was still just a handful of people who are actually ready to vote. Gets multiplied by 4. What are you thinking of? Yes, Edward Lee.
I'm just plugging in numbers. So if we had,
Oh, okay.
maybe like it was 2, and then square them would be 4, but if it was 4.
Well, yes. So I think what you're thinking, you can tell me if this is wrong, is that, well, the total energy, I could calculate the total energy at any point during an oscillation because it doesn't change. So let's do it where it's going to be as easy as possible. And it seems pretty easy the total energy, there's no, when I stretch it out to x equals 2a, and release it from rest, there's no kinetic energy there. So the total energy is just the potential energy, right? So before we had a total energy of 1/2 Ka squared. Now we've got a total energy of 1/2 K times 2A quantity squared. And when we square that, we get an overall factor of 4 compared to what we had before. So stretch it double, you don't just double the energy, you quadruple the energy. And that's because of that square in the formula. You stretch it, you double the stretching distance, you quadruple the amount of energy stored in there. And that's because, the spring doesn't pull very hard when you stretch it a little bit, but then it starts pulling really hard. And so you stretch it the same distance, you put a lot more energy into it because the force is getting stronger. Any more questions about that one? We're just kind of reasoning about the formula here. Okay, there's a couple more here. The only thing that was changed is what's underlined and bolded there. Do the same thing, double the amplitude. By what factor does the maximum speed of the mass get multiplied compared to the case we were considering originally? Let's see a vote on that one. See what my vote is. Still that everybody's very hesitantly holding up fingers, but I'm seeing a lot of B's there. What's the reasoning for B? Yes. Yeah, you double the amplitude, you're going to double this quantity. So it goes twice as fast at the center. Despite the fact that you got 4 times as much energy stored in the system, that comes out as twice as fast because, of course, the kinetic energy, if you double the V, you're going to quadruple the kinetic energy, which will then quadruple the total energy stored in there. Okay, one final one associated with this. What about the maximum acceleration of the mass? The mass is oscillating back and forth. We haven't thought too much about things that are oscillating like that, this back and forth on the x-axis, say, in terms of their acceleration, but you have enough information from what we've talked about to reason about the maximum acceleration of the mass. Let's see a vote on that. Again, I'm not getting a strong vibe from the class, but it's okay. It's been a while since we talked about springs. I'm seeing a few hands going up for B. I agree, B. The argument is if you know F net, you know AX. F net X, you get AX, right? The spring force law that, maybe it's been a while since we talked about it, was called Hooke's law. And it says, if you orient the usual things where the convention is X equals 0 is when the spring is relaxed and the stretching direction is the positive X direction, then Hooke's law says that F net X, the spring force X component is equal to minus Kx. In other words, when you stretch it to a positive X direction, the spring is pulling back in the negative X direction. That's what the minus sign is about, where K is the spring constant. In any case, the maximum acceleration is going to be when the force is maximum, right? Because this is the only force that's resulting in the acceleration. So if we're thinking of the sum of the force X components equals max, whenever the net force is maximum, that's when the acceleration is going to be maximum. And the net force is maximum at the biggest and smallest X values, right? The extreme points there. And so that means that if we have X equals A, we've got a certain force there. If we double X, we're going to double that maximum force, and therefore we're going to double the acceleration. So again, the answer, I agree, is B. Okay. Part of that is just to remind us about Hooke's law and reasoning about the potential energy associated with it, and so on. Okay. This is the, I thought I put this in here, but I guess I didn't have it in the right place to do it. Okay. The author you saw in the reading also derives something about the period of a mass spring system. This is a little bit harder to get out of it, and I didn't want to go through the complicated derivation that the author does, but this is something that you'd be given on your equation sheet on the next exam. Okay. T is the period. So the claim is here, we can at least experimentally verify this, and you'll do this in lab if you didn't already do it on Tuesday. It depends on the mass and the spring constant. The bigger the mass, the bigger the period. That means it oscillates more slowly, right? A big period means it takes longer to oscillate. So let's just look at that. Bigger mass means bigger period. Bigger K, that means a more stiff spring, one that's harder to stretch, corresponds to a smaller period according to that formula. So let's try to verify those, at least just looking at this mass spring system that we've got here. I know it's a little bit complicated because gravity is involved. We'll talk a little bit later about how we can kind of ignore gravity in these kinds of systems, but it's too hard for me to make it oscillate horizontally. So let's just try to get a feeling for what the oscillation period is. And notice it also says that the period of oscillation is independent of the amplitude. Then A didn't appear in there. And so that means if I just pull it down a little bit, let's try to, I'm just going to say down every time it reaches its lowest point, so we can kind of get the rhythm of how fast the period is changing, right? So small oscillation, down, 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 down. Let's do a slightly bigger oscillation. Down, 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 down. Same thing, even if you do a tiny oscillation. The spring's gotten all. Let's try to just pull it down a little bit. Down, down, down. So it looks like it doesn't depend on the amplitude. And those of you who did the lab yesterday found that out. The claim was that it also depends on the mass. And the bigger the mass, the bigger the period. That means it takes longer. So we kind of got the rhythm of this one with this mass. Down, down. Let's try it with a larger mass. Oh gosh, I'm going to have to get this off the end of the table. I bet it's going to go below the edge. Keep that rhythm in your head. Okay, you might not be able to see this so well, but maybe I'll pull it up. Down, down, down. Longer period, right? It's taking longer to go there. So that's the dependence on the mass. The dependence on the spring constant. You might think, well, it's hard to change the spring constant, but actually it's kind of not too hard to make a spring, make something out of this with a larger spring constant. Notice the more coils I have right here, the easier it's going to be to stretch it. If I hold some of the coils in my finger and only allow like 7 coils here, it's a much stronger force for me to stretch it, 10 centimeters or something, compared to taking this whole thing and stretching it 10 centimeters. There's just a lot more slack there. So one way for me to create a spring with a larger spring constant is for me to just hold some of the coils up there. So if you kind of remember the original, well, let's just do it again. Down, down, down. Now I'm going to hold this up here and, hold a lot of the coils up. Down, 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 down. So I'm just created a spring with a larger spring constant by doing that. And it at least qualitatively agrees with the formula that we see there. Okay. Okay, those were the demos I wanted to do. And now, okay, I forgot, I have a worksheet. It's a good thing. Let's pass out the worksheet. And let's do problems, just problem 1 on this worksheet. Which, let me just orient you to it a tiny bit, and then I'll put this formula back up on the slide there. The idea is you're given, and this, for those of you at home, is on the website for today. I'm going to make a plot of position as a function of time of the oscillating mass on the spring. Of course, it's going to be up and then it's going to be down. It's going to be up and down. Maybe I hold a 2-meter stick here, like maybe you did in lab, and measure at each time very carefully what the x coordinate is. And it, of course, it goes up and down as time goes on. Not surprisingly, we'll show later on that it is a sinusoidal kind of curve, like a cosine or a sine kind of formula like that. And we're asked various things on this worksheet, like what is the amplitude of the oscillation? Well, you're given some points on the curve, the XY coordinates in meters and seconds, right? The sort of, I guess you're given the T and X coordinates on here. And so you can kind of just read off what the period is. You can kind of read off what the amplitude is. From the from the period, you can get the frequency. So we're just practicing with some of these things. The Vmax, I erased it from the board, but we were asked about the maximum speed. That was root K over M times A. Maybe I'll put those formulas up on the board while you're working on it. So we're just doing problem one, all the parts. And let me put those two formulas up here since I don't have them showing anymore. The period of a mass spring system is 2 pi times root M over K. And we said that the maximum speed is equal to root K over M times A. So notice the crucial thing is those coordinates there. The first coordinate is always the horizontal one. That's the way you're doing it in your math classes, right? So that first point at the top of a hill there means that the T coordinate is 8/13 of a second. Okay, I think hopefully you're told, I think I marked X is in meters and T is in seconds, hopefully, yes. And the 5/7 at the top of the hill means that the X value there is 5/7 of a meter. So you got to use those little points that are given on there to figure out what's a period, what's the frequency, what's the maximum speed, and so on. I'm going to try to mark those points on this kind of rough graph I did here. Paula, how's it going? So the amplitude, you want to think about, from the distance along X from the highest position to the lowest period is 2 amplitudes, right? Because the amplitude is how far from the middle to the top. So you need this distance right here from the bottom to the top is 2 times the amplitude, and you can get that from those coordinates on there. Frequency X. The easiest thing to do is to say, I know this is all new, but the relationship between frequency and period's easy to read off there. That's how long for one in time for one down up cycle, right? The relationship between frequency and period is reciprocals of each other. So this is in cycles per second, this is going to be, sorry, this is in seconds, how many seconds per cycle, then this is going to be in how many cycles per second, which is hertz, Hz. Maybe I'll put my answers up on the board while you're working. Questions, anyone? Yeah. So you're using the period equals 2 pi times root m. M is 1.2 over k, and then solving for that, right? So here, presumably you've divided by 2 pi on both sides to get this number. Something's gone wrong there, right? Because 2 pi is about 6, and this number is already less than 1. It looks like you did multiply, yeah. Yeah, that's certainly a way to get at it. Anybody else have questions?
I have 2 questions actually.
Yeah, go ahead.
I'm kind of confused. Like, the x component of the like points. I guess like I get what the y component is because that's just the height, but like the whatever number has a denominator of 13, I don't understand what that is.
Yeah, so that's, this is like x, y coordinates, but here, what we're calling x is the horizontal coordinate. So this is in seconds, and this is in meters. So
Gotcha.
5/7 is meters. So it's oscillating between 5/7 and 1/7 of a meter. So it's not oscillating about x equals 0 in this case,
Of
for
course.
whatever, that's how we've held our meter stick, and it just happens to be oscillating between some positive values. And then we can see the times here. The period is the amount of time between 8/13 and 20/13. That sounds like 12/13 of a second is the period. And therefore, the frequency is the reciprocal of that, which is 13/12. Does that help, Grant?
Yes, significantly. Thank you.
Dr. Kelly,
Yes.
for D, it asks like at what time is it at V max? How would we find that?
Well, in this case, we know that the maximum speed occurs when it's passing the middle position, right? That's when there's no potential energy in the spring and it's all in kinetic energy. So you've got to figure out at there are lots of times when it's passing the middle. That's when it's not at the top of a hill, it's not at the bottom of a valley, but it's halfway up, right? So if
Yeah.
you're looking at those points, that would be like, you could give this time here, that would be a correct answer. You could give this time here, that would be a correct answer. You could give this one here, that would be a correct answer too. And you can just sort of compute those by going halfway in between the time associated with the top of a hill and a bottom of a valley, right?
Yeah.
So I would say 8/13, and we're up to 14/13. So that's 6/13 between there and there. So this time is 3/13. I have to add on to 8/13. So it looks like one possible answer would be 11/13 of a second. I don't know why I made such tortuous fractions for this, but it came from another worksheet that was really for another class, and I wanted to reuse the graphic.
All right. Yeah, that clears it up.
The amplitude is not 4/7 because the amplitude, remember, when we have something oscillating, there's a question about why isn't the amplitude 4/7? And it is true, it's going, the distance between its lowest point and its highest point is 4/7. But the definition of the amplitude is from the middle position, how far to the highest position or the lowest position. And so in this case, this is 5/7, this would be 3/7 and 1/7 down here. So the distance from 3/7 to 5/7 is 2/7. So it's not the full range from up to down, it's from the middle to the top or the middle to the bottom. You just divide by 2. All right, let's, just tell me if you have questions about this. Are there any more questions about the amplitude? Should we go through that? I was just talking about it seconds ago. The only other tempting answer is 4/7 of a meter, which is how far from the highest position to the lowest position. That's 2 amplitudes. The amplitude is the distance from the middle position where it's zooming past to either the highest or the lowest. So it's only 2/7 of a meter. The frequency is most easily gotten from the period. They're reciprocally related. So I read the period off here. The period is how much time elapses, say, from the highest point to the next highest point, okay, or the maximum x to the next maximum x. That is 12/13 of a second, and that means the frequency is 13/12 hertz. Okay, and that's 13/12, just a little bigger than 1, so I just wrote it as a decimal there. C, what's the spring constant of the spring? That's probably most easily gotten, or the way that pops out is the period, right? We said the period is 2 pi times root m over k. I'm given m, we just read the period off of there, and so I'm going to solve this equation for k. Anybody want to see the details on that one?
Yeah. Because I use that same equation, and I don't know if I'm using the wrong period or my algebra is wrong.
Okay, so our period is 12/13. So we have 12/13 equals 2 pi root m is 1.2, is that right? And so I'm putting all SI units in over k. And my job is to solve for k. So I could take this number, divide by 2 pi, and then maybe take the reciprocal, and then maybe I'll write it down, and then I would square both sides and multiply by 1.2. We can do it together. Actually, I didn't bring my calculator, unfortunately. Do other people agree with my number here? Yes? Okay. Yeah, so probably the easiest thing to do when you're looking for something in the denominator, often what I'll do is just take the reciprocal of both sides, and then the thing you're looking for is in the numerator, right? So I could, if 2 things are equal, their reciprocals are equal because they're exactly the same, right? So I could certainly write this as 13/12 equals 1 over 2 pi, that's the reciprocal of 2 pi, times the reciprocal of this, which is root k over 1.2. And now I say, okay, that's easier to dig out the K. I multiply both sides by 2 pi, I square both sides, and then I multiply by 1.2. Okay, D was what's the maximum speed the mass ever attains, and I'm just, plugging into this formula. We now have a K, we now have M, and we've computed A, so we can just calculate with that. Any questions on that one?
For the time part, I know you said it's like anytime it passes the middle.
Oh, yes, I forgot that was asked. Give one time at which it has the speed. Right, so the idea is as this is oscillating back and forth, it's when the spring is totally relaxed, that there's no potential energy stored in the spring, and that's when the kinetic energy is going to be maximum. That means V is going to be maximum.
Is that like, does the middle times like slow down those time? Or does the middle, sorry, that was really confusing. Does like the speed on like the middle line slow down though as time progresses?
Well, it would for a real system. Again, I'm imagining this is oscillating horizontally and there's no friction, there's no air resistance. And in that idealized case, no, it wouldn't. We're imagining it just keeps oscillating. The amplitude doesn't decrease as time goes on. For any real system, of course, the amplitude is going to get smaller as time goes on. And that means the maximum speed is going to get smaller as time goes on, as the amplitude slowly goes down. But we're ignoring that. Good question. E, if we double the mass attached to the spring, what's the period now? How do we reason through how the mass affects the period? Well, here it is right here. We're keeping the same spring constant, right? And so if we replace m by 2m, that's multiplying the right-hand side by a factor of square root of 2. So we take our period that we found before, which was 12/13, and we multiply it by root 2 and calculate that number. Apparently that's 1.31. All right. Good. Boy, time is short, but let's see what's next. Okay, let me show you a simplification. Maybe this is a good place to end today. This system that I have been showing you here, which is not the same as that horizontally oscillating system on a frictionless table. The point of making it oscillate horizontally is that there's no gravitational potential energy. And the system I'm considering here has two forces involved. There's a spring force, which, right now this mass is just sitting in equilibrium. There's a spring force trying to pull it up, which exactly balances out the weight force, which is going down, and it's in equilibrium. So in no way, in our usual way of talking about springs, should I be labeling this position as x equals 0, because the spring is definitely not relaxed. It's not in an equilibrium spring position. The spring is stretched and it's trying to pull up. The book shows, and it's a little bit it's pretty complicated. It's nothing but algebra, but it shows that the following is true. When you hang a mass from a spring, of course, both gravity and spring forces are acting when it's sitting at rest, sitting in that equilibrium position that I was just showing, where it's not oscillating, it's just sitting there. Nonetheless, through some work, you can show that you can pretend that this new position that it's at equilibrium in, with both the spring and gravity sort of balancing each other, if we call that point x equals 0. It's not the x equals 0 we were using before, but let's now call that x equals 0 and measure x positions from that new equilibrium position, which is a balance between gravity and spring. If we do that, then we don't have to keep track of the gravity part at all. In other words, I can pretend when I'm doing this that if I stretch it down from this new equilibrium position by 2 centimeters to calculate the force that the spring is, it's as if there's only a spring force on it, and the magnitude of the spring force is k times 2 centimeters. And the potential energy stored in it is 1/2 times k times 2 centimeters squared. Of course, there's gravitational potential energy involved, and the spring is actually stretched much more than 2 centimeters from its equilibrium. But it's a great simplification, and it just takes a little bit of work to show that that's true. And I think you do need to know that, memory serves, in one of the homework problems that I'll put up for chapter 11. So keep that in mind. It's as if we're going to pretend, this is kind of like our torque pretending all the mass is centered at the center of mass, even though we know it's not true. I can just ignore gravity completely and pretend there's just a spring, and the spring, it's as if it's relaxed, right, as I have it right here. And I'm only going to take into account spring potential energy and spring forces as I move from that new equilibrium position. It takes gravity out of the equation, which really simplifies things tremendously when you're doing energy types of calculations. Okay, so I'm just going to say, if we choose to measure X from the new equilibrium position, we can use our old formulae for for spring potential energy and spring forces. And maybe that's a good place to stop. We will on Friday finish up that worksheet, and then we're going to start in on fluids. Just don't worry about it for the exam. Just let it wash over you. And we'll have to see what we're going to do Monday. This past Monday, I had a worksheet that we never got to because we were doing those homework problems. Remember, I said, oh, I have a worksheet with some extra practice problems. I think what I'm going to do, since we're supposed to give you an extra assignment instead of break day, I'm going to give you that assignment, which is great practice for the upcoming exam. And you can do it well ahead of break day this weekend, and it'll be a great timing to do it before the exam. So I'm going to email it to you. I'll also probably put it on our website. And as usual, I will put up solutions so that you can compare too, but try it yourselves first. I saw there's some momentum problems on there, and lots of the newer material that we've been doing too. All right. If I don't see you tomorrow, I'll see you on Friday. And again, I apologize. I have a meeting right after today, so I cannot stay today. Please come see me in office hours tomorrow if you need homework help or want to talk about other stuff.